Did you all see the message?
Yep.
Yeah.
You're all getting back in? Okay. All right, good. So 161, we talked about something where if I'm given an array, and I'm not going to get all 17 in here, of numbers, and I start putting numbers in, and this is going to be an array of size 17, and it just goes on and on and on. And I'm going to put in unique numbers from 1 to 100. For example, 45, 57, 2, 3, 6, 98, 99, 41, and so on. And I said, okay, so we stored all those arrays. I know it's of size 17, which is one of the issues we've been dealing with in the course is memory size with the arrays. And that's why linked lists work so well sometimes. But if I got ready and said, is the number 82 in here? Well, we did something called a linear search, if you recall. And a linear search started at the beginning and went all the way across looking for the number. Big O notation says, worst case scenario, I would have to check all 17 spots of the array. Sound familiar?
Yep.
Thank you. Binary search was the other one that we looked at. But in order to do a binary search on this list, and it doesn't seem like it makes much sense to do it yet, but in order to do a binary search, the first thing we had to do was sort. And then once it was sorted, I went to the middle position and looked to see if it was higher or lower. Big O notation, that brought in, though, what kind of worst case scenario would be the sort plus, if it was a sorted list and I search, what is it? 2 to the n? Sound familiar?
Yeah.
What was it for linear search? Big O notation for linear search was
O of n.
O of n, right? Because we had to start and go all the way through the list. Worst case scenarios, I have to hit them all. Binary was big O of,
Nth power.
say again?
Was it to the nth
Yep.
power? Or
2 to
was
the
it
nth power, right? So we have all these different things going on with big O notation, and we start to see efficiency. But again, it's the, I have to have a sorted list in order to do this. Well, hash tables is going to give us a whole nother way to do faster sorting other than the two that you just looked at. And this is where one of the things in this course is that I start to like a lot. We start looking at bizarro ways to do it. In my mind, I'm thinking linear and binary, how else could you possibly do this? Well, we're going to take a look at something called a hash table today. And in order to do this, we need to do something along the lines of, well, what if I change my array size? Okay. If there are 100 numbers, or 17 numbers, and they're unique from 1 to 100, what if I did an array of size 100? And we've talked about this before, how size has become a common all caps written so we know what the size. Now, let's start putting numbers in. What if I put in 45? Well, where did you put in 45 before? In the first slot, right? But what if this time I went over and I put 45 in the 45th slot? What if I put 57 at index 57? What if I put 2 at index 2, and so on? Now, what do I have? Well, I have what's called a hash function. If I get ready to go and do retrieval, I have an immediate, boom, I can go find it right away, right? Is 24 in the list? Well, I'd go to subscript 24, see if it's in the list. If it's in the list, great. If it's not, it doesn't do me any good. So now my search has cut way down to immediate time, 1. What's the problem with creating a table creating an array of size 100 when I'm only putting 17 numbers in?
Wasting memory.
Yeah, I'm wasting memory. I'm only using 17% of the memory that I laid out. So what we're going to do now is we're going to start to take a look at, what if I change the size of the array? And what if I strategically put in the numbers into the array? Okay, well, let's do this once. Let's take an array of size 17 again. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I can go all the way out, 11, 12, 13, 14. I need a couple more. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so good. This guy would be subscript 0. This guy would be subscript 16. All right, so now I'm going to put in unique numbers from 1 to 100, but instead of filling from left to right, I'm going to fill strategically. So let's say my first number is 45. What I'm going to do here is apply a hash function. And a common hash function is going to be something that is going to involve modulus. For example, I might take the number and I might mod it. And in this case, I'm going to mod it with 17. And in a minute, I'll explain why I'm picking certain numbers. Okay. So if I take 45 and I apply this hash function, function f of I equals I mod 17, what do I get for a remainder? What's 45 mod 17?
11.
Thank you. 45 mod 17 equals 11. So I'm going to go and put that in. Now, we have these numbered from 0 to 16. I got a chat. Is that for me? Yay, chat? Chat says, oh, yes. Say it out loud. That way we can move along a little bit faster. Okay. So I'm going to go to the 11th spot. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And I'm going to put in my first number, which was 45. Now, if I go to retrieve it, I can find it pretty quick. I just apply the hash function again. Okay. Next number in my list was 57. Where would 57 go? 57 mod 11 gives me a
2.
2. 0, 1, 2. So I'm going to stick the 57 in here. My next number is a 2. What is 2 mod 17?
I forgot if it's just 0.
No. No. How many times does 17 go into 2? None. How many do I have left? 2. 2 mod 17 equals 2. So I get ready to play. Uh-oh, I can't stick the 2 there. So now what do I do? Well, the next thing that comes into play is a term called probing. And what we're going to do with our program probing is go linear, which says, I want to put the 2 in. The 2 is already filled, so I'm going to stick it to the right. I'm going to put the 2 beside it. Okay? So now if I have to, and I want to see if 2's there, I'm going to jump in and say, 2 mod 17 is 2. Uh-oh, it's filled, but that doesn't mean it's not in the list. It may be to the right because that's the kind of probing I'm doing. Now, as I start to get numbers side by side, I get another term comes into play called clustering. I start to develop clusters. Okay, so now I'm starting to think code-wise. I could put another number in, 3. Oh, crap. I know where 3 should go. 3 should go right there, but I'm going to have to move it over to there because its location was filled. Okay. The next number was 6. I'm going to take, oh, that's a 4, excuse me. I'm going to take 6. That's going to go in the 6 location. So I start to see what's going on. Now I need to have some conversation. When I started with all of this, how did I know if one of these was empty? Well, I'm going to need to fill my array at the very beginning with what? What would be a number I could put in to the array when I initialize it to start?
-1.
Yeah, -1's going to work, and that's what the book uses as well. So this guy should be filled with -1s moving all the way across. Okay, sounds pretty good. So if I get a new number, my next number was 98, and 98 is going to go where? 17 and 17 is 34, double to 64. If I subtract 64, I get 34. Oh, nice. 98 is going to go in the 0 spot. So far, so good. What if I had 16? Where would 16 go? Out here on the end, right?
Yeah.
Yeah. So if I had 16, it would go here. What if I then said, okay, there's 16. My next number is 33. Where would 33 go?
Slot 0.
Uh,
Oh,
well,
sorry. I'm wrong. I'm thinking of the wrong number.
you're close. Where would it go? Well, you would think it would go here because mod 17 puts me here, but then I have to loop around. So now I'm going to check here. It's not available. I would check here. All right, everybody's with me so far. So what have we done up to this point? Well, we've taken a look at how would we insert into a hash table, okay? So we're gonna have, oh boy, a couple of things going on here. Insert being one. All right, let me go back to my hash table. We've been talking about inserting. We have clustering occurring, and we have this linear probing where we moved along. Now, as I look at this guy, I think, well, what's going to happen after I put 17 numbers in? It's going to be filled, right?
Yeah.
Yeah. So what happens if I say, I'd like to find out if a number is in, and I do the hash function, and I land here, and then I need to do linear probing to find it. And all of a sudden, if it's full, I have to check here, 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 wrap around here, 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 because it could be sitting there. So what's my worst case scenario again?
ON.
Yeah, no different than the linear search. So one of the things that we do in order to make this work a little bit better is when we have all these collisions happening, right? They collide and I have to move to the right. So there's another term. I have collisions going on. And then I have the linear probing where I move to the right and I start to form clusters. One of the things I'm going to do is I'm going to change the table capacity. So instead of having 17, if you read this in the book, and I've read it a couple other places, ideal number to have is 1.5 to 2 times the size. Okay, so 1.5 times 17 is, somebody help me out, approximately. Half of 17 is 8. Double it is 34. So give me a number between 25 and 34.
30.
Okay, 30's good guess, but I'm going to say no 30. Trying to fix my camera here a little bit.
31,
Why 31?
because it's odd.
It's odd. Hey, welcome, Jake. Another reason that I would pick something of like 31 is, remember this guy up here was of size 17, and what did I mod by? 17. So when I do this, I'm looking somewhere 1.5 to 2 times the size, and I want to have a prime number, because a prime number is going to let me access any of my, in this case, we said 31 locations. So when I'm doing it, one of the ways to improve performance is to know how many numbers I need. And in this case, I need like 17 of them. But when I store it in an array, I want to go with an array size of 31. That's going to help eliminate some of the collisions. It's going to eliminate some of the clusters, and we'll still go along with the probing. Now, a second way, so this is the first way to improve performance. Second way to improve performance. Let me get, can you see me now? Improve performance. The first we said is table size. A second one might be to, when it comes to this clustering, instead of doing a linear probe, okay, what if I did a different type of probe? So different probing. So instead of going one to the right, one to the right, one to the right, what if I do, and an example that you'll see is, what if I do squares? Like I'm going to do 1 squared, so I'm going to check 1 to the right. And then I might check -1 to the left, because that's still 1 squared. Then I might try 2 squared, which is 4 to the right. Then I might try -4, which is 4 to the left. So instead of keep putting them side by side, I may be jumping around, putting them at different spots. A third way to improve performance is to put on a second hash function. So right now we were looking at a hash function of f of I equals I mod 31. Okay, what if I did another hash and I did something like, my second one would be f of I equals 31 minus, you could start making up anything here. 31 minus I mod 31. I need equations, though. They're going to make sure that I get the numbers from 0 to 31. So whatever these are, I still need to fall within that range of 0 to 31. So 3 ways to improve performance. What a great test question that would be. All right, let's come back to our list. And we started looking at inserting, and we're like, okay, great. I need to start the array out, fill it all with -1s, and then if I go in, I hit a spot. If it's -1, I stick the number in. If it's not -1, I'm going to do linear probing till I find a -1 and stick it in. If I'm at the end, I'm going to wrap around with my linear probing and keep going until I find a spot to put it in. Pretty good? Everything's good so far? Okay, so that's some of the idea behind insert. Now, what if I take a look at this and say, okay, insert's not so bad. What happens if I want to delete? If I want to delete, all right, I'm going to come back to my list and I'm going to say, let's delete 2. Okay, so I'm going to come into 2 and say, that's not 2, but that doesn't mean I'm done. In fact, I'm going to keep moving along until I find a what? A -1. If I find a -1, I know it's not there. if I find a 2, what would I like to put there?
A -1.
Okay, so a suggestion was, let's take this out and put in a -1. So I'm starting to think delete. I want to go to the location with my hash function. I want to do a linear probe over. And if I find that I put in a -1, and if I keep doing my probing and get to a -1, I know that it's not found and I can't delete it. Sound pretty good? Okay. What if I have this list of numbers? Okay, and I'm at ... I'm at subscript 4. Okay, and this is just an example. What if my hash function is mod 31, and the first number I put in is 4. The second number I'm going to put in is 35. Oh, that would go there, but it's not. So linear probing, I'm going to move to the right. The next number I put in is, anybody want to guess what I'm going to say?
4.
Nope, 4 is already in. I'm going to put in 66. Okay? So far, so good. Now, I get ready and I say, ooh, let's search. I want to delete 35. If I want to delete 35, I jump, I mod it with 31, I land at 4. I come over and say, oh, there's 35. You're going, put in a -1. Well, now what if my next line said, I want to delete 66? I go to my 4, and then I say, nope, it's not there. I move over 1 and see -1, and I'm thinking, uh-oh, I reached that -1. It doesn't exist. Solution. What can we do? Because I know I want to, I'm sorry?
You'd have to look after the number you want to delete and see how many numbers there are that aren't -1 and then shift them all over to the left.
Oh, you want to do some shifting. We wouldn't want to do that because something out here, 14, might be in its 14th spot. You know, this guy might be in its proper spot. So this is 5, 6, 7. 7 might be here, and the next one is -1. We'd lose the 7. Good guess.
Well, how could it tell the difference then between like a 7 and then like another number that has a mod of 4?
Okay. We would still do the linear probing until we reach that -1. Now, that doesn't solve our problem here that once I deleted something. Simple solution. Come in here. When I delete, I'm going to put in a -2. So what that's going to tell me now is -1s are empty. Anything with a -2 in is empty. But if I'm probing, if I'm looking, I check 4. Nope, 66 isn't there. I check here. Nope, 66 isn't there, but don't stop because it's not a -1. Move to the next one. Now I found the 66. I can delete it and put a -2 in there as well. So not only are we going to work with -1s in this situation, we're also going to work with -2s.
Wouldn't that like cause some inefficiencies? Like if you have a 3 before the 4 and you're trying to delete something after the 3?
If you have a 3, well, hopefully that's fixed by our size being big enough. You know, we said we're storing 17 numbers in an array of size 31. So when we're doing that, it'll eliminate some of that clustering, making your probing pretty efficient.
Happy with that.
You go with that? Okay. Coming back up to the top. So delete's kind of interesting. Traverse. Traverse. How would we be able to use traverse here? Well, what would traverse be? I mean, remember we talked about traverse, and we had traverse doing a lot of different things, okay? In our situation for today, for a hash table, we're going to just use traverse as a search, okay? So the traverse is going to be a little bit like delete, but it's going to be a little bit easier if you see what I'm talking about. And finally, a fourth one would be called display. So the 4 functions that I'd like to have for my hash table are insert, delete, traverse, which is just searching for a number, and display. Everybody's good? Yeah?
Yep.
Yeah.
Okay. All right. Here's what I'm going to do. We're going to take a look at traverse and display. We're going to write pseudocode for it. Then I'm going to break you up into 2 groups. One group's going to do the pseudocode for insert. One group's going to do the pseudocode for delete. Now, the pseudocode that we write for these 4 are the pseudocode that you're going to be using in your hash table program. So whatever pseudocode we come up with for these 4, you all have to use that for the code in your program. Same names, same everything. Let's start with display. That should be the easiest one. Display. We shouldn't go with capitals, should we? Notice I'm doing this in pencil. Well, let me ask you this. One of you last week had a nice whiteboard you pulled up. Who was that?
Whiteboard.
Yeah, you had a screen that your breakout room was using.
I know they have the tools.
Yeah, Vasily, your group was using it. And Kyle, was that you? You and Jake's group?
Yeah.
Yeah. Did you like what you had to do by hand, or should we go with the other one that Vasily's group was using? Okay, then I'll just
exactly by hand?
I'll just write for display. All right, so display. Will I be passing anything in?
We're displaying everything, so
So
no.
I'm going to pass in an array, right? Y'all are giving me the pseudocode for the algorithm or for the function you're going to write. We're going to call everybody's is going to be called display. What are we passing in?
The array.
Array. Give me a name.
ARR.
ARR. What else do I need in here? Do I need to pass the size in?
No.
No. Are we going to assume we know it's 31, or are we writing a display for an array that should be generic for any array? Like you may have a display already written. Should we pass in size, or is there a function that I can use that tells me the size of the array?
Maybe it'll be better if we use pass in the size.
Pass in the size? Okay.
Yeah.
We're going to call it lowercase size. Now, you can put in your ints and so on later, because remember, this is, right now we're working with integers. Right now we know it's a size 31. Okay, so I come in. Tell me give me some pseudocode here.
Start at 1 or to the end, to the size.
Is
like
this a
4
loop?
int.
4.
Yes.
Give me a variable name.
Int I0.
Okay, I'm going to do this. I'm going to put int up above. Now,
Then
reason why,
0.
right? Reason why is there are some versions of C++, some versions of Java that won't let you declare a local variable in the for statement. So a good habit would be to get it out of there. Int I equals 0.
0.
I is, excuse me. I should be doing this in pencil. I is
Less than size.
less than size.
I plus plus.
I plus plus inside of here.
See out.
Just to see out. That goes this way, right?
Mm-hmm.
And then array sub
I.
Display's pretty easy. Straightforward, but that's what everybody's going to use. You're going to call it ARR. You're going to call it I.
So you want to display all the negative ones in there as well?
Yep. Yep. So you're going to make this a little fancier in this actual C outline, because I made a comment, and I think a lot of you saw it, how boring some of your programs are. Man, are they boring. You asked me to type in a baseball team. I have to go through and type in New York Yankees, and I typed it wrong. Then I did it again and typed it wrong. Wouldn't it have been easier to just use numbers? Somebody say yes.
Mm-hmm.
Yeah.
Yep.
Yeah. Wouldn't it be nice if there was some color on some of these pages? Wouldn't it be nice if the old guy didn't have to squint because the font's so small? And I think on the next program, I'm going to make that part of the grade. Call it pizzazz, and I think you all know what I'll be talking about. The next one we wanted to write was traverse. Traverse. I'm going to bring in an array. I'm going to bring in the size and
Search element.
the search element, right? What do you
Or
want to call
key.
it? Key? Key. Everybody's going to call it. This guy up here was a void. What about, so up top I made it a void. And
This
down
could
here,
be
we're going to
not
we're,
bool.
Why not
Could be
Boolean?
just be void too.
Why not Boolean?
Okay.
Okay. I'm going to come in. I'm going to return. Give me a
True.
Boolean name.
False.
Yeah, give me a variable name for Boolean.
Yeah.
Good.
Found.
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 I know I'm going to have to give found a starting value, right?
Which is false.
Okay. What else?
Same kind of scenario with the display. Start in I equals
In
0.
I, okay. For I equals 0, I is less than size, I plus plus.
Now it wouldn't mess up with the clustering and all of that, would it? When you're traversing through again.
Now we're going to
No.
traverse through until it's found or not. So
All right.
you're third semester, folks, right? Do we really need this guy?
Nope.
No, let's cross him out, because, where am I going to have an issue? With the for loop, aren't I? I'll let it go this time.
The break.
Well, it's not a break. We'll put a return inside of here.
Yeah.
So what am I doing? I'm going to come in here, and if it's found, I'm going to return true. If I get out of here, I'm going to return false. Everybody's okay with that?
Mm-hmm.
All right. What's going on inside? If.
Key matches ARR of size. All right.
Very good. If key is equal to, better put the double equal to in there, right? Array sub I,
Mm-hmm.
return
True.
true.
That's it.
All right. So either you take a quick shot of this with your phone. I don't know if I can get it all in. Can you see all of it? Take a quick shot of it with your phone, or you're going to have to come back to watch the video.
Recording.
Watch the recording.
Done.
Okay. So now what? We need two more. We need insert,
And delete.
and we're going to need delete. One of the things I'm going to tell you right now is I recommend you have the drawing. As we went through and learned about this, we were drawing all of these arrays and we were putting numbers in. So hopefully you have something going on like that. What I'm going to do is break you up into groups. When your group is done, I want you to post the pseudocode that you came up with on the discussion board. I'll actually take a picture of these other two that we're going to require and put them on the discussion board. So I'll take a picture of that, put it on the discussion board. Otherwise, I'm going to put you into breakout rooms right now. How many do we have? 11. So we're about 5 and 5. And one group is going to do insert, and one group's going to do delete. So once you're in your rooms, I'll come tell you which one you're going to do. And then when you're done, post it. And then when you're done, we're done. Questions?
Do we have like a predetermined hash function?
Let's just go with mod 31.
Okay.
All right. So I see what you're saying. Put in 31 for now. And then when you guys write the program, it might not be 31. It might be another number you can substitute in.
And we're going to have like the same size, like 17. Okay.
That can be changed when you write the actual program later. Good questions. For display and traverse, we were able to write them generic. Okay. Stopping the recording.